we're wanting to find, I'll do a couple of things here. So we've got a rectangular box with a base length twice its width, and we're made of 48 square meters of metal. Show that the height is given by this expression. Okay, this is a typical kind of maxima problem. So we've got a rectangular box. Alright, so let's just do a little sketch here. Okay, now its length is twice its width. So if this is x, say, that's its width, then its length will be 2x. H is the height of the box. Now, we want to show that the height is given by this expression. So it's made with 48 square meters of metal. Okay, we can probably assume that this is an open box. So the surface area, because that's what we're dealing with here, the surface area is going to be given by total surface area. We've got 2x times h, and there's two of those, so it's 2 times 2x h. And we've got x times h. Okay, so we've looked at that side. Okay, those two sides. And then we wanted to look at now this side here, which corresponds to that side there, and that's x. So I'm going to go 2 lots of those, and it's x h. And then the bottom, underneath, just one of those, is going to be 2x times x, which is 2x squared. Okay, so it doesn't actually say that it's an open box, but we'll see. We may need to add an extra one. We'll see what we end up with. Now, we know our total surface area here is 48 square meters. So 48 equals, now that's 4xh plus 2xh plus 2x squared, and that then simplifies to, that's 6xh plus 2x squared, and we're wanting to solve for h. So 6xh will equal 48 minus 2x squared, and then divide by 6x. So that's 48 over 6x minus 2x squared over 6x. Okay, I can see that I'm not going to end up with the same thing, so let's just change a little something here, because we can assume then that's going to be a full covered box then. Okay, so it's going to be 2x squared times 2, so that gives us 4x squared. Right, so let's just change that to 4x squared. Change that as well. That's going to be 4x squared, and that will be 4x squared, as is that. 4x squared. Right, now let's simplify. So we have h equals 48 over 6 is 8. So that's 8 over x minus, and we can cancel here that common factor of 2. So that cancels with that, leaving us with 3. So we end up with 2x squared over 3x. Actually, I should have cancelled the other at the same time, because we've got that x cancels with that, one of the x's on top. And so you can see we have what we are required to find. So that's a typical kind of question you have, where you need to show something like this, because that's going to be necessary to when it comes to the next part of the question. Okay, so part B says express the volume V in terms of x. Now, we know the volume is given by length times breadth times height, or length times width times height, which in this case is going to be x times 2x times h, or 2x squared times h. Now, we don't want there to be three variables in our volume function. That is why we need to use this expression for the height. So what we need to do then is replace our h here with this expression, which is in x. So that means we can write v equals 2x squared times 8 over x minus 2x over 3. And so we have volume is equal to, that's going to become 16x minus 4x cubed over 3. So that is our volume expression in terms of x, part B. Now part C says find the maximum volume. So, once again, we're going to use calculus. So maximum volume, think of this as a volume function, okay? If we're plotting v against x, then this is a cubic, right? Probably going to be, shaped something like that perhaps. Well, not exactly like that, but it doesn't really matter. The point is we're wanting to find where the maximum is going to be. So that's going to correspond to our turning point. So stationary points are found when our derivative is equal to 0, so we're going to find dv dx, which will be 16 minus 3 times 4 over 3, which gives us 4x squared. So that's our derivative function, and we want then to do so our stationary points occur when our dv dx is equal to 0. Therefore, we're going to let 16 minus 4x squared equal 0. So that means 4x squared will equal 16, x squared equals 4, x will equal plus or minus 2. Okay, now because this is a nice straightforward polynomial function, we could easily find our second derivative, 2v dx squared, which will be negative 8x. So, if x equals negative 2, then dv 2v dx squared will be negative 8 times negative 2, which is 16, okay, which is positive, which means it is concave up, which means it's a minimum value at that value of x. Now, it's not going to be very relevant anyway, because this x value is a negative value, which in terms of the problem doesn't make any sense. Okay, so, but it's just worthwhile just in terms of remembering our understanding of how this works. Okay, and so just confirming then, if x is equal to positive 2, then d2v dx squared is equal to negative 8 times positive 2, which is negative 16, which is concave down, which corresponds to a maximum value. So that confirms that the volume is a maximum when our x value is equal to 2. So going back to the question, it's asking, go away, it's asking us to find the maximum volume. Okay, so just go back up because I want that equation. Right, so we know that maximum volume occurs when x is equal to 2. That means our maximum volume is going to equal 16 times 2. I'm just using this volume equation here. 16 times 2 minus 4 times 2 cubed over 3, which is 32 minus 4 eighths are 32 over 3, which is, okay, so that's 96 minus 32, which is 64 over 3, okay, which, okay, if we just get a decimal value on that, 32 minus 32 over 3 is 21.3. Okay, which is 21.3. It is meters, isn't it? So that's actually cubic meters. Of course, that is an approximate value for that. Okay, there we go. And that's how we solve that problem. Okay, so typically you are required to just confirm using calculus whether it's a maximum or a minimum, even if we know by the nature of the function itself what it would be. Let's make sure that we are doing it properly. Okay, all right, I think that's it. And so these are the problems you can go on with for that exercise and working on those problems. Thank you very much.